A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Herman, I had a really frustrating afternoon yesterday. I was trying to get one of the newer frontier models. I think it was the latest GPT-5 preview, to help me draft a comprehensive technical manual for that old solar array we have on the roof here in Jerusalem. I fed it everything. The original specifications from 1998, the wiring diagrams, the maintenance logs from the last 10 years, even the thermal imaging reports. It was a massive amount of data, probably close to 300,000 tokens, and the model read it all perfectly. It could answer specific questions about the inverter's serial number or the voltage drop on string 3. But when I asked it to actually write the full manual, including the troubleshooting steps and the safety protocols for the high voltage DC lines, it just stopped. It gave me about 6 pages of really good, high-quality content, and then just cut off mid-sentence.
Ah, the classic 4,000 token wall. Or maybe you hit the 8,000 token ceiling if you were lucky. It is the bane of every power user's existence right now, Korn. It is the great irony of the current AI era. We are living in the year 26. We have models that can ingest the entire works of Shakespeare, the legal code of the European Union, and your solar manuals in a single breath. We have these massive buckets for input, but we are still forced to use a tiny little cocktail straw for the output. It is like being able to read the entire Library of Congress in an afternoon, but only being allowed to write a postcard in response.
And that is actually what our housemate Daniel was asking about in the prompt he sent over this morning. He noticed the same thing. We see these headlines every week about context windows expanding to 1 million, 2 million, even 10 million tokens in the case of the latest Gemini updates. But the actual output limit, the amount of text the AI can generate in a single go, seems stuck in the dark ages. Daniel wants to know why this bottleneck exists and why, even when the model is still within its advertised limits, the quality of the writing starts to fall apart. He called it coherence decay.
Herman Poppleberry here, and I am so glad Daniel brought this up because it touches on the fundamental physics of how these models actually work. It is not just an arbitrary software limit that some developer at OpenAI or Anthropic set because they were feeling stingy with the compute or wanted to save on their electricity bill. There are deep architectural reasons why writing a book is infinitely harder for an artificial intelligence than reading one. It involves the very nature of autoregressive generation and the physical constraints of the hardware we are running these things on.
It really does feel like a bait and switch sometimes. If you tell me a model has a 2 million token context window, the average person assumes that means the model can handle 2 million tokens of total conversation, back and forth. But in reality, that capacity is almost entirely dedicated to the memory of the input. When it comes to the creation side, we are still hitting these hard ceilings. So, Herman, break it down for us. Why can we read a library but only write a pamphlet? Why is there such a massive gap between what the model can see and what it can say?
To understand this, we have to look at the difference between how a model processes input versus how it generates output. When you feed a model a massive PDF, it uses something called parallel processing. Because the entire input is available at once, the transformer architecture can look at all those tokens simultaneously, more or less, and build a mathematical representation of the relationships between them. This is incredibly efficient on modern hardware like the NVIDIA Blackwell chips or the newer Rubin architecture we are seeing roll out. But generation? Generation is a completely different beast. Generation is autoregressive.
Autoregressive. That is one of those terms we hear a lot in the technical papers, but let us unpack what it actually means for the user experience. Why does that specific word lead to my manual getting cut off?
It means the model produces exactly one token at a time. It predicts the next word, then it takes that word, appends it to the previous sequence, and predicts the next word after that. It is a serial process, not a parallel one. If you want a 10,000 word output, the model has to run 10,000 consecutive inference cycles. Each cycle depends on every single word that came before it. This creates two massive problems that define the output bottleneck: latency and error propagation.
Let us talk about error propagation first, because that explains the coherence decay Daniel mentioned. I have noticed that if I ask for a long story, by page 10, the characters start changing names, or the plot just starts looping back on itself. It is like the model is getting tired or losing its mind. It starts off brilliant and ends up sounding like a broken record.
That is a great way to put it. Think of it like a game of telephone, but the model is playing the game with itself in a hall of mirrors. Every time the model chooses a word, it is picking from a probability distribution. It is not choosing the right word with 100% certainty, it is choosing the most likely word based on its training and the current context. If it makes a tiny 1% deviation from the ideal logic at token 100, that deviation becomes part of the truth for token 11. By the time you get to token 4000, those tiny little statistical wobbles have compounded into a massive logical drift.
So it is a cumulative noise problem. The model is essentially hallucinating based on its own previous slight hallucinations. It is building a house on a foundation that is slowly tilting further and further to one side until the whole structure collapses.
Mathematically, this is linked to the accumulation of probability errors in the softmax layer. In a standard transformer, the attention mechanism is trying to weigh the importance of every previous token. Over long sequences, the narrative vector or the logical thread gets buried under the weight of its own previous choices. The model's focus starts to blur. It is not that it forgets the beginning of the prompt. It can still see your instructions in the context window. It is that the path it has taken to get to the current word has become so noisy that the original instructions are no longer the strongest signal in the mathematical space. The model becomes more interested in being consistent with its own recent mistakes than being consistent with your original goal.
That is fascinating. So the soft limit Daniel mentioned, where the quality drops off before the model actually hits the token cap, is really a stability issue in the latent space. It is a math problem. But what about the hard limit? Why do the APIs for the top-tier models often cap out at 4096 or 8192 tokens? Surely, if I am willing to pay for the drift, they could just let it keep running?
Well, that brings us to the hardware side of the house, and specifically something we talked about back in episode 1081, the KV cache. KV stands for key value. When the model is generating text, it stores the mathematical representations of all the previous tokens in its high-speed memory, the HBM or high bandwidth memory on the GPU, so it doesn't have to recompute them every single time it generates a new word.
Right. I remember that discussion. You called it the invisible memory tax.
It really is a tax, and it is a progressive one. As the output gets longer, that cache grows linearly. It takes up more and more space on the GPU's memory, but more importantly, the time it takes to attend to that cache increases. This leads to latency spikes. If you have ever used a web interface for an AI and noticed that the typing speed gets slower and slower the longer the response gets, that is the KV cache bottleneck in action. For a provider like Microsoft or Google, letting a single user generate a 50,000 word response isn't just a matter of electricity, it is a matter of tying up incredibly expensive hardware for a long time. That GPU could be serving dozens of other users who just want a quick email summary.
So there is a massive economic and throughput incentive to keep outputs short. They want you in and out as fast as possible. If they let the model run for 20 minutes to write a novella, that is a huge opportunity cost for their data centers. It is essentially a denial of service attack on their own efficiency if they allow massive single-turn outputs.
And when you factor in the global lead in this technology right now, it is a strategic resource management issue. We have the best chips, but even the best chips have limits when you are serving millions of people simultaneously. There is also the issue of the agentic throughput gap, which we dove into in episode 1078. When you have autonomous agents like the ones people are using for coding or research, trying to perform complex multi-step tasks, they hit this same wall. They run out of working memory or coherence runway before the job is finished. They start looping or repeating the same command because the noise in the output has overwhelmed the signal of the task.
It feels like we are in this weird transition period where the models are smart enough to understand the whole task, but the engine isn't built for long-haul flights. I mean, if I want to refactor a massive code base, the model can see the whole thing in its context window, but it can only write the changes for 1 or 2 files before it starts making syntax errors, or just giving up and saying, insert rest of code here.
And there is another factor here that people often overlook, the training data. This is where the human element comes in. Think about the internet, which is the primary source of training data. Most of the data these models are trained on consists of short to medium length snippets. Blog posts, comments, news articles, even research papers are usually broken into manageable sections. There is very little gold standard training data that consists of a single, coherent, 50,000 word logical chain written by a single person in one go without any subheaders or breaks.
That makes total sense. If the model mostly sees human writing in chunks of 500 to 2,000 words, it learns that a thought usually ends around that point. It doesn't have a strong internal model for how to maintain a single narrative thread for 50 pages because it hasn't seen enough examples of that being done perfectly in a way that maps to its token-by-token prediction style.
Precisely. And it gets worse during the supervised fine-tuning phase, or SFT. During SFT, humans are often the ones rating the outputs. A human rater isn't going to sit there and read a 30,000 word output to check for logical consistency across the whole thing. They are going to rate shorter, punchier responses. So we are effectively training the models to be short-form thinkers. We are rewarding them for being helpful in the first 500 words, not for being coherent at word 10,000. We are literally optimizing for the bottleneck.
So it is a triple threat: architectural limitations of the transformer, hardware costs of the KV cache, and a lack of high-quality long-form training data. But let us get into the practical side for a minute. If I'm a developer, or just a guy trying to write a technical manual for a solar array, what do I do? Daniel mentioned Frankenstein chunking methods. Is that really the only way to get a long document out of an AI in 2026?
For now, yes, but you can be much smarter about how you do it. One of the best strategies is what I call chain of thought checkpointing. Instead of asking the model to write the whole manual, you ask it to first generate a detailed outline. Then you ask it to write section 1. Then you feed section 1 back into the prompt and ask it to write section 2 based on section 1.
But wait, doesn't feeding the previous sections back and just eat up the context window and eventually lead back to that same drift or noise problem? If I keep feeding it more and more, won't it eventually get confused anyway?
It can, but here's the trick. You don't feed the whole thing back in. You feed a state reset prompt. You provide the high-level outline, a summary of what was just written in the previous section, not the whole text, and then clear instructions for the next section. You are essentially clearing the model's mental workspace and giving it a fresh starting point that is still tethered to the main goal. You are using the massive input context window to store the memory of what has been done, while keeping the output task small and manageable.
I like that. It is like giving the model a save point in a video game. You are saying, okay, we have successfully reached this far. Forget the messy details of how we got here. Just remember these 3 key facts and move on to the next level. It keeps the narrative vector fresh.
You are forcing a realignment. Another practical takeaway is to stop asking for the whole thing. If you need a long output, ask for it in segments of precisely 2,000 tokens. Write the first 2,000 tokens of this report. Then, write the next 2,000 tokens. By doing this, you are staying well within the coherence window where the model is most stable. You are essentially acting as the external attention mechanism that keeps the model on track.
It is interesting that we have to manage the AI's attention span, almost like you would a child's. You have to break the big task into bite-sized pieces. But Herman, what about the future? We are seeing new architectures being discussed, things like state space models or Mamba, and even Jamba from AI-21 Labs. Do these solve the output bottleneck? Is there a version of this show in 2027 where we aren't talking about chunking?
They are certainly trying to solve the quadratic complexity problem. In a standard transformer, the computational cost grows quadratically with the sequence length. In a state space model, or SSM, it grows linearly. This means you could, in theory, have much longer outputs without the same latency and memory penalties. However, there is a trade-off. So far, we haven't seen an SSM-based model that matches the raw intelligence or reasoning of the top-tier transformers like GPT-5 or Claude 4. They are great at remembering long sequences, but they struggle with the deep, complex logic required for something like your technical manual.
So we are at a bit of a crossroads. We have the smart models that are stuck with short outputs because of their architectural overhead, and the fast models that can handle long sequences but aren't quite as brilliant. It feels like the next big breakthrough in artificial intelligence isn't going to be about adding more parameters or more training data. It is going to be about solving this stability and memory issue.
I agree. We need a hybrid approach, maybe a transformer brain for the reasoning paired with an SSM memory or some kind of recurrent mechanism that allows the model to maintain its state without the KV cache ballooning out of control. There is also some very cool research into speculative decoding. This is where a smaller, faster model, a drafting model, predicts what the larger model is going to say, and the larger model just verifies it. This can speed up generation significantly, which might make longer outputs more economically viable for the providers. If the big model only has to work on every fifth token, it can stay active for much longer responses.
That is a clever workaround. It is like having a fast-talking assistant draft the email, and the boss just gives it a quick thumbs up or corrects a word here and there. It saves the boss's time, or in this case, the expensive GPU's time.
But until those architectural shifts become mainstream, we are stuck with the Frankenstein methods. And honestly, Korn, as a conservative when it comes to systems design, I kind of appreciate the chunking approach from a different angle. It forces a level of human oversight. If you just hit a button and a 50,000 word manual pops out, are you really going to read the whole thing to make sure the safety protocols for those solar panels are correct? Probably not. By forcing the user to generate it section by section, it encourages a trust but verify workflow.
That is a very fair point. There is a danger in one-click long-form generation. We already have enough issues with AI-generated slop, filling up the internet and academic journals. If it becomes effortless to generate entire books in a single prompt, the noise-to-signal ratio is going to plummet even further. Maybe the output bottleneck is a hidden blessing, keeping us tethered to the process and ensuring we are actually looking at what is being produced.
It is a friction point, and friction often leads to better quality control. But I do think for technical tasks, like your solar manual or for complex coding projects, the bottleneck is a genuine hindrance to productivity. We are currently in a situation where the AI can think of a solution that is too long for it to speak. That is a frustrating place to be. It is like having a brilliant idea, but only being able to explain it in 10-second voice notes. You lose the nuance, you lose the connective tissue.
And speaking of connective tissue, I want to go back to what you said about drift and hallucination over long sequences. Is there any way to mathematically steer the model back on track mid-generation? If we know it is going to drift, can we just nudge it?
There is. Some researchers are working on top-down guidance systems where a separate, smaller monitor model watches the output in real time. If it detects that the output is drifting away from the original prompt's intent or the logical constraints, it can actually adjust the probability weights for the next token to nudge the model back toward the goal. It is like a rumble strip on the side of the highway. If the model starts to veer off, the system gently steers it back into the lane. This is part of the agentic throughput solution, giving agents the ability to self-correct before they hit the wall.
That sounds incredibly promising. If we want an AI to manage a complex project over several days, it needs those rumble strips. Otherwise, it will eventually just wander off into the woods. It is the difference between a tool and a partner.
Precisely. This is the agentic throughput problem in a nutshell. We need systems that can maintain state over long periods. Currently, our agents are like goldfish with the vision of an eagle. They have a huge vision via the context window, but a very short memory of what they were actually doing 5 minutes ago in the generation process.
So, for our listeners who are hitting this wall, let us recap the practical advice. 1. Don't ask for the whole thing at once. 2. Use a detailed outline as your North Star for every subprompt. 3. Use state reset, prompts where you summarize the progress and clear out the noise from the previous turns. And 4. If you are a developer, look into modular architectures where different parts of the task are handled by separate API calls.
And I would add a 5th, manage your expectations about the advertised context window. Just because a model can read 1 million tokens doesn't mean it can reason across 1 million tokens with perfect clarity, and it certainly doesn't mean it can write anything close to that. Treat the context window as a library you can reference, not a workspace you can fill with new writing in one go.
That is a crucial distinction. The 1 million token headline is about retrieval, not creation. It is about how much data you can dump in, not how much wisdom you can get out in a single breath.
And honestly, Corn, I think we are going to see a shift in how these models are marketed. Eventually, the output limit will be just as big a headline as the input window. We will see models boasting about 50,000 token coherence or novel length generation stability. That is the next frontier. We are moving from the era of big memory to the era of big coherence.
I hope so. I really wanted that solar manual in one go. But I guess I will have to stick to the chunking method for now. It is a bit more work, but it does force me to actually read what the model is producing, which, as you pointed out, is probably a good thing for safety protocols. I don't want to find out on page 42 that the model decided to swap the positive and negative leads because it got bored.
It usually is a good thing, especially when you are dealing with high voltage wiring on a Jerusalem rooftop. You don't want a hallucinated ground wire or a safety protocol that involves imaginary circuit breakers.
Definitely not. Well, this has been a fascinating deep dive into the output wall. It is one of those things that seems like a minor annoyance, but actually reveals so much about the underlying physics and economics of artificial intelligence. It is a reminder that we are still in the early days of this technology.
It really is. It is a reminder that even in this era of magic technology, there are still fundamental constraints of math and hardware that we have to respect. We are building these incredible engines, but we are still learning how to build the fuel tanks and the exhaust systems to handle long-distance travel. We can go fast, but we are still working on going far.
Well said. And hey, if you are listening and you have found your own clever workarounds for the output bottleneck, maybe you have a specific prompting template or a script that handles the chunking for you, we would love to hear about them. You can get in touch through the contact form at myweirdprompts.com. We are always looking for new weird prompts to explore, just like the one Daniel sent us today.
And if you are enjoying the show, please take a moment to leave us a review on Spotify or your favorite podcast app. It really does help other people find the show, and we appreciate the feedback more than you know. We have been doing this for over 1,000 episodes now, and it is the community that keeps us going. Your reviews are the signal that helps us cut through the noise of the podcast charts.
It really is. Check out the website at myweirdprompts.com for the full archive and the RSS feed. We have covered everything from the KV cache in episode 1081 to the agentic gap in episode 1078. There is a lot of deep dive content there if you want to go even further down the rabbit hole of how these models actually function.
Thanks for joining us today in Jerusalem. It has been a blast.
This has been My Weird Prompts. We will see you in the next one.
Until then, keep those prompts weird and your outputs modular.
Goodbye, everyone.
Take care.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes